Hello friends, welcome to the video tutorial on Firebird 5 robotics research platform. This platform is based on ATmega2560 microcontroller, which belongs to AVR architecture based microcontroller family. In this tutorial, we will study the ADC interfacing on Firebird 5 robot. Now let us consider the agenda of discussion in this tutorial. This includes the mechanism of operation of ATmega2560 ADC with the description of various ADC channels. We also use ADC interfacing on Firebird 5 robot, which includes the initialization and configuration of various ADC registers. So, what is ADC? It stands for Analog to Digital Conversion. Why is there a need for ADC? Firebird 5 has 8 IR proximity sensors, 5 sharp IR sensors, 3 white line sensors, battery voltage sensors. All these sensors give analog output. We need to use ATmega2560 microcontroller ADC to convert these analog values into digital values. Let us now see the features of inbuilt ADC of ATmega2560. The ATmega2560 features a 10-bit successive approximation ADC. The resolution of the ADC indicates the number of discrete values it can produce over the range of analog values. So, the resolution is expressed in bits. It takes 13 to 260 microsecond conversion time. The ADC block is connected to 16-channel analog multiplexer, which allows 16 single-ended voltage input from the pins port F and port K. The device also supports 14 differential input channels. The ADC has an optional left adjustment for the result readout. The reference voltage for the ADC indicates the voltage range for the ADC. Vref can be selected as either a VCC, internal 1.1 volt reference, or 2.56 voltage. The ADC operates in two modes, free running mode and single conversion mode. The ADC can also be enabled using the interrupt. Now let us see the ADC channel of ATmega2560. As you can see in this table, we have 16 single-ended voltage input from the pins of port F to and port K, which are connected to pin number 82 to 97. Each of these channel has a devices connected to it, so that the values from each of these device can be read in a digital format using the appropriate channel number. Let us now look at the steps for using the ADC in ATmega2560. The steps required for the ADC are as follows. Step 1. Enabling ADC. Set the ADEN bit of ADC control and status register ADCSRA to logic 1. Step 2. ADC Prescaler division ratio. Set the bit ADPS of the register ADCSRA, which sets the frequency between 50 kHz to 200 kHz. Step 3. Selecting the reference voltage for ADC. Select the reference voltage for ADC as AREF by making the reference register 1 and 0 as 00. Left adjustment. ADCH has two most significant bit and ADCL contains the remaining 8 bit. We left shift this data so that ADCH will contain the 8 bit including the MSB and ADCL will contain the remaining 2 LSB. The first step of the program is always the initialization. So let us begin with the ADC initialization. To program the ADC, we have to initialize some registers before we use. These registers are ADCSRA, ADC and control register A, ADCSRB, ADC and control register B, ADMUX, ADC Multiplexer Selection Register, ACSR, Analog Comparator Control Status Register. All these registers are 8-bit. We will now study each of these registers in detail. Now let us see the first register ADCSRA, which is ADC Control and Status Register. The bit description of ADCSRA is as follows. Bit 7 ADEN, ADC Enable, Writing 1 to this bit will enable the ADC. By writing 0 to it, the ADC is turned off. Turning off the ADC while a conversion in progress will terminate the conversion. So, the initial value of this bit will be 1. Bit 6. ADC start conversion. In single conversion mode, writing 1 to this bit will start the conversion. When conversion is complete, it returns 0. So the initial value of this bit should be 0. Bit 5. ADC auto trigger enable. When 1 is returned to this bit, auto triggering of ADC is enabled. The ADC start conversion on positive edge of the selected trigger signal. Here we are not using any trigger, so the initial value should be 0. Bit 4. ADIF ADC interrupt flag. This bit is set when ADC conversion complete and data registers are updated. So here the initial value of this bit should be 0. Bit 3. ADIE, that is ADC interrupt enable. When 1 is returned to this bit and when SRAG is set, the complete interrupt is activated. Here we need no interrupt to get activated, so the initial value of this bit should be 0. ADPS ADC Prescaler Selection Bit. This bit determines the value of the division factor between the crystal frequency and the input clock of the ADC. By default, the successive approximation circuit requires an frequency between 50 kHz to 200 kHz. The prescaling is set by ADPS bit in ADCSRA. Here the frequency of Firebird is around 11 to 14 MHz. Thus the division factor we require is 64. So the initial value of this bit should be set as 110 as per the factor given in the table shown in the next slide. So the final value of the ADCSRA register is 0x86. As explained about the prescaler in the previous slide, here the table shows the various prescaler bits that should be used depending upon the division factor. For the Firebird 5 robot, the division factor should be 64. The value that should be assigned to ADPS bit in ADCSRA is 6, that is binary 110. Now let us see the second register ADCSRB, that is ADC Control and Status Register B. The bit description of ADCSRB is as follows. Bit 7 reserved bit. This bit is used for the future use, so the initial value of this bit should be 0. Bit 6 analog comparator multiplexer enable. This bit is used to enabling the comparator multiplexer, but here we are not using it, so the initial value of this bit should be 0. Bit 5 and bit 4 reserved bit. This bit are reserved for future use, so the initial value of this bit should be 0. Bit 3 MUX analog channel selection bit 5. This bit together with the MUX 420 are used to select the channel in combination with the analog input that is connected to the ADC. If this bit is changed during a conversion, the change will not go in effect until the conversion is complete. This bit is used when we are using the channel number greater than 7. So the value that is assigned depending upon the channel number. Here the initial value should be 0. Bit 2 to 0, that is auto trigger source. If ADAT bit in ADCSRA is returned to 1, the value of this bit select the source trigger on the ADC conversion. This bit are used to select the trigger source. So here the initial value of this bit should be 0. So the final value of the register ADCSRB should be 0x00. Now let us see the third register ADMUX, that is ADC Multiplexer Selection Register. The bit description of ADMUX is as follows. Bit 7 6, that is reference selection bit. As shown in the next slide, this bit select the voltage reference for the ADC. If these bits are changed during the conversion, the change will not go in effect until this conversion is complete. The internal voltage reference option may be used if an external voltage is applied to the ARF pin. So to select the A reference voltage, here the initial value is 0 0. Bit 5, ADC Left Adjust result. The ADLAR bit affects the presentation of ADC conversion result of the ADC data register. When 1 is returned to ADLAR bit will affect the result as a left adjust. Otherwise the result is right adjusted. Here we are using the ADC left adjustment. So the value of the ADLAR bit should be 1. Bit 4 to 0, analog channel and selection bit. The value of this bit select the combination of the analog input connected to the ADC. So the initial value of this combination of analog input should be 0 0 0 0. So the final value of the ADMUX resistor is 0x20. As explained in the previous slide, the table shows the bit of 76 to be set while changing the reference voltage. If the gain voltage is selected, then only 2.56 voltage is set as an internal voltage reference. For differential conversion, only 1.1 volt can be used. Here we are using A ref, so the value of this bit should be 0 0. Now, why do we need ADC left adjustment? When a ADC conversion is complete, the result is stored in two resistors, that is ADCL, ADCH, as shown in the figure. When ADCL is read, the ADC data register is not updated until ADCH is read. Consequently, if the result is left adjusted and no more than 8-bit precision is required, it is sufficient to read ADCH. Otherwise, the ADCL must be read first and then ADCH. The ADLAR bit in ADMUX and the MUX register affects the result that is being stored from the register. If ADLAR bit is set, the result is left adjusted. If the ADLAR is cleared, the result is right adjusted, as shown in the figure. So to retain the maximum appropriate value, we just read ADCH and set the ADLAR bit. The ADMUX selection represent the values to select the channel for conversion. As explained in the Firebird 5 robot, we have 16 single-ended channels. So the table here shows the value of the bit to be set to select the appropriate channel. The important thing to note here is that the first 8 channel number are represented using the binary notation, and the remaining 8 channels have the MSB bit set, and the rest represent the normal binary notation. So these bits are used to select the proper channel for conversion. Now let us see the last register, that is ACSR, analog comparator and status register. This register is used for analog comparator. The bit description of ACSR is as follows. Bit 7 ACD, that is analog comparator disable. When 1 is returned to this bit, the power to the analog comparator is switch off. This bit can be set by any time to turn off the analog comparator. Here we are not using the comparator, so to disable it, the value is 1. The remaining bit can be used only if the comparator is enabled, otherwise they are set to 0. So the final value of the resistor ACSR is 0x80. Now let us look at how to write the program. The program starts with the initialization. So we first configure the port. The port used in the ADC are port F and port K. We need to configure this bit as input pin. Thus the value of the port will be 0x00, and also enable the pull-up resistor using the port resistor. The next function is used for the ADC initialization. Here in the ADC init function, we set the value of the resistor of ADC. The values to be assigned are as follows: ADCSRA 0x00, ADCSRB 0x00, ADMUX 0x20, ADCSRA 0x86, ACSR 0x80. Let us now begin with the syntax for the C program. The standard C program begins with the including of header file and the main function. In the main, we configure the port using the init devices. We have the infinite while loop which we are using to print the sensor using print sensor function to display the values of ADC obtained on the LCD. Here we are using the channel number 012 and reading the various sensors channel number connected on the Firebird 5 robot. As you can see, the function of the print sensor defined, which obtain the values using the function ADC conversion, which is defined in the next slide. So the values obtained after the conversion is stored in the LCD print to print on the LCD. This function is used for the conversion of analog to digital values. This function takes the value of char as an input, which is the channel number where the conversion is to be done, and after the conversion it returns the char value obtained after the conversion. In the function initially we have a if condition to select the appropriate channel number which are above 7. Using the ADMUX register we set the value of left adjustment, and then using the ADCSRA register we set the conversion bit. The while loop is used to wait for the conversion to complete. The condition used in the while loop is until ADIF flag is set. The value obtained after the conversion is stored in ADCH register, which is then transferred to temporary variable A. The value of ADCSRA and ADCSRB are again set, and the value obtained is returned to the calling function. Thus, using this function we can obtain the digital values from the analog sensor through use of the appropriate ADC channel. Now let us look at the demonstration of using the C program of ADC interfacing. So click on the ATmega Studio 6. Here follow the steps for creating the new project as demonstrated in the documentation of ATmega Studio 6. Here I have already created a project and written a program for ADC interfacing. So let us now look at the program for ADC interfacing. To start with, we have an hash defined f_CPU 14745600. This is the crystal frequency at which the robot is operating. So you may define this at the start of the program. Then we have the header files, that is hash include avrio.h, interrupt.h and delay.h. We also have an header file lcd.h. This header file is user defined. This file is given by us in the folder name header files. You need to copy these header files in the folder of your project. Then we have the variables defined for reading the values of the ADC. Let us now study the configuration of the pin. We have LCD port config. We are going to use the ADC interfacing and print the obtained value on the LCD. So we need to configure the LCD port. Next we have the ADC pin config. As we know, the channels of ADC are connected to port F and port K. So here we set the values of port F and K as an input pin. We call the functions of port config in the port_init. As we have already studied about the ADC registers, so in the function ADC_init we set the initial values of the registers to be used for ADC. Next we have the ADC_conversion function. This function takes the char value, that is the channel number, as the input, and after these steps of conversion it returns the value a char. This value is the digital value obtained after the conversion at the corresponding channel number. So the steps followed are already explained in the tutorial. We have the print sensor function. This function is used to print the value obtained after the ADC conversion on LCD. It takes the input as row, that is the row number of the LCD, the column number of LCD and the corresponding channel number. We use the lcd_print function, which is already defined in the header file lcd.h. The init_devices, which is used to call all the initialization functions in it. Now we look at the main function. In the main function we initialize all the functions which are used for the initialization. Then we have a infinite while loop. In this while loop we have used the print sensor function and called it 3 times. Here we have used different channel number. As you can see, the channel number 1, 2 and 3 represent the white line sensors of the robot. So we are going to read the values of the white line sensor. So this is all the program about. Now we will build the program using the build option, that is build solution. Here you can see the output window at the bottom. It has built successfully with 0 errors. Now we are going to load this program on our robot. So open the bootloader file. Now switch on your robot and set the robot in the boot mode, that is press the boot switch and then press and release the reset switch and then release the boot switch. Now your robot has gone to your boot mode. Then select the various configuration in the bootload, that is select the COM port. In my case it is COM7. Then select the baud rate, that is 115200. Then the microcontroller, that is ATmega2560. Here you need to browse the file, that is the hex file that we have created now. It is always in the debug folder. Here you can see the hex file. So browse the folder. Now click on the program button and wait for the program to get loaded on the robot. Here as you can see, the program has successfully been loaded on the robot. Now switch on the robot and again you can see the values on the robot. Here you can see we have only used 3 sensors, so you can see the values that is been printed on the LCD. You can demonstrate and obtain different values by keeping the white line sensor on different surface and obtain the reading, like keep on the white surface and then change the surface to black and obtain the various reading of the ADC. So here we have completed the demonstration of ADC interfacing. So here we have successfully understood the mechanism of operation of ADC of ATmega2560 and programmed the ADC interfacing on Firebird 5 robot. With this we have come to an end of this tutorial. Thank you for listening. For any queries or doubt, you can visit qa.e-yantra.org. This is Shailesh Jain signing off.